You may remember that in the foundation course, we looked at the sort of curves you get when you cut a cone with a plane. For example, in this case, we get an ellipse. Well, if the plane was actually horizontal, then what I get would be a circle, but that's just a special case of an ellipse. Now, what happens if I tilt the plane a little bit more? Well, in this case, we cut the cone with a plane which is actually parallel to one of the sides of the cone, and what we get is a parabola. That's a curve that goes on forever. Now, it looks as if I continue to tilt the plane, well, nothing new is going to happen. But that's not quite right, because you've got to think of the cone as being extended upwards. And in this model, we've actually extended our cone upwards. And then you can see that if the plane is tilted a bit more, then what we're actually going to get is an interesting curve which is in two pieces. That's called a hyperbola. Well, these three curves are called conic sections: the hyperbola, the parabola, and the ellipse. However, if I had actually sliced this cone with a plane which actually went through the vertex, this is called a vertex, well, in the case of the hyperbola, I would have got a pair of straight lines and not a nice curve. And in the case of the parabola, if my slicing plane was parallel but went through the vertex, then I get a single straight line. And in the case of the ellipse, my slicing plane going through the vertex would give me a single point. Well, I suppose these points and lines must be called conic sections too, but they're degenerate conics. And in this program, we'll only be interested in non-degenerate conics, that is, the genuine curves. Now, it turns out that in coordinate geometry, all conic sections, degenerate or non-degenerate, can be described by an equation of the second degree. That is, it's an equation of the form ax squared plus bxy plus cy squared plus fx plus gy plus h equals 0. And in fact, in this program, we're going to take as a definition of a conic an equation of the second degree.
If, as Alan said, we agree to restrict ourselves to curved conics, then any second-degree equation you plot will have a nice form like these three curves here. But you'll be very lucky if it turns up symmetrically situated with respect to the axes, like these are. And what we're going to do in this program is show you that any equation you plot can be transformed by moving the axes, so that when the axes are in these positions, the equations have simple forms. In the case of the ellipse, the equation will come out in the form x squared over a squared plus y squared over b squared equals 1. And you'll have met an example like that in the pre-work with specific numbers for a and b. In the case of a hyperbola, we have a very similar equation, as you might expect, only now it's x squared over a squared minus y squared over b squared equals 1. And again, you'll have done a numerical example in the pre-work. The final case is that of the parabola, where you'll see that the equation can always be reduced to this form, y squared equals 4ax. That's very nice. We have three curves, and when the axes are in the right positions, we have three equations. And to show us how this reduction can be done, David's going to take a typical numerical example of a second-degree equation.
52x squared minus 72xy plus 73y squared minus 32x minus 74y plus 28 equals 0. Well, that really is very long and very complicated, and it tells you virtually nothing, and that's one reason why I've chosen it. But we can still get some idea of what it looks like by plotting a few points and sketching the graph. Well, I've done that, and my guess is that we have an ellipse here. But no amount of plotting will actually prove that it's an ellipse, because, well, there may be some weird bumps or corners which the sketch isn't accurate enough to show up. And in any case, we've defined an ellipse by a certain form of equation, and we've proved nothing until we've shown that our equation can actually be transformed to one of the appropriate type. Well, if this is an ellipse, then the standard position for the axes should be about there. And one way to get this new pair of axes is to start with the old ones and first translate and then rotate. And if the curve's an ellipse, then its equation relative to these new axes must have this form. But you see, our equation is very different. It has this term involving x, y, and also these linear terms, one involving x and one involving y. So all three of these terms must disappear when we change the axes. Well, first, let's try the translation. Suppose we move our axes to here. For a point xy, there will be new coordinates x dashed, y dashed. The curve can now be described by a new equation in x dashed and y dashed. The values of the coefficients will depend on how far we've moved the axes. Remember, we're trying to make b, f and g 0. But how do we get from one equation to the other? What's the relationship between xy and x dashed, y dashed? Suppose our new origin is at the point alpha, beta. Now, x is equal to this distance plus this distance. X equals x dashed plus alpha. And similarly, y equals y dashed plus beta. So to get to the new equation, we take the old one and write x dashed plus alpha for x and y dashed plus beta for y. Well, that's a bit tedious, but not very difficult. When you do it and collect up terms, you'll find that the first three coefficients are never changed by a translation. So to make this equation more like the standard ellipse, we'll have to try and make f and g 0. And if you work it out, you find that this happens when alpha equals 1 and beta equals 1. Well, this tells us where to put the axes. And h turns out to be minus 25. Now, the origin seems to be in the centre of the ellipse, and this is reflected in the algebra. If we take a point on the curve and take a line through the centre, then the point which is the same distance on the other side of the centre is also on the curve. And this is geometrically what we mean by centre. Algebraically, if our point is x dashed, y dashed, the point on the other side is minus x dashed, minus y dashed. If we look at the equation, minus x dashed squared is the same thing as x dashed squared. And minus x dashed times minus y dashed is the same thing as x dashed times y dashed. And the same sort of argument applies to minus y dashed, all squared. So, the equation tells us that minus x dashed minus y dashed is also on the curve. Well, if you work it out, you'll find that that can only happen if there are no linear terms. So, algebraically, no linear terms means geometrically that the origin is at the centre. Well now, our next move is going to be to rotate the axes, but just before we do that, there's one snag that you may come across. In this example, we were able to get rid of the linear terms, but there are some cases when you can't do that.
In fact, I've got an example here. The simplest example of the parabola, y squared equals 4x, where I've taken a to be 1. When we translate the axes to the point alpha beta, the equation becomes y dashed plus beta all squared equals 4x dashed plus alpha. Now we can leave beta equal to 0, so there'll be no linear term in y dashed. But the right-hand side of the equation will be 4x dashed plus 4 alpha. And whatever we make alpha, that 4x dashed will still be there. And that isn't surprising. We discovered that getting rid of the x and y terms is the same as moving the origin to the centre. But where is the centre of a parabola? The curve is obviously symmetric about this line. So if there is a centre, it must be on this line. Well, how about this point? If we take this point on the curve and look an equal distance on the other side of our candidate for the centre, we're not on the curve. That will always happen unless this point could be the centre. But again, if we take any point on the curve and look an equal distance on the other side of the centre candidate, we're always off the curve. And that proves that a parabola has no centre. That's not really a problem, it's an advantage. The parabola is the only curved conic without a centre. So we know that if we can't get rid of the linear terms, we have a parabola. And we've given you a worked exercise to do after the programme to show that if you can't get rid of the linear terms, then you can reduce the equation to this form, y squared equals 4ax. So David knows he hasn't got a parabola, but he still hasn't reduced his equation into the standard form for an ellipse.
Right. You see, we still have this term x dashed, y dashed. And so if the curve is to be an ellipse, then the rotation we're about to do must get rid of this term. Well, now let's have a look at the algebra for a rotation. We'll rotate the axes through an angle theta. The point x dashed, y dashed will now be the point x double dashed, y double dashed. It turns out that x dashed, y dashed and x double dashed, y double dashed are related by these equations. And you can verify this later if you like. So we substitute into our equation and get a new equation in x double dashed and y double dashed. We won't introduce any more linear terms because of course we're rotating and the origin stays at the centre. Now we're trying to lose the x double dashed times y double dashed term, and that means making b 0. Well, b turns out to be 7 sine 2 theta minus 24 cos 2 theta. If we make b 0, we get tan 2 theta equals 24 over 7. And this tells us how far to rotate the axes. The new equation is x double dashed squared plus 4 y double dashed squared equals 1. The axes now seem to be sitting on the axis of symmetry of the curve. That is, if this point is on the curve, then so is its reflection in the x-axis, and also its reflection in the y-axis. If the first point is x double dashed, y double dashed, then the second is x double dashed minus y double dashed, and the other one is minus x double dashed, y double dashed. And of course this shows up in the algebra. If you make x double dashed into minus x double dashed, there's no change. And similarly for y double dashed. Of course, this couldn't happen if the equation still contained an x double dash times y double dash term. And now, of course, if you haven't already spotted it, the equation is in standard form with little a equals 1 and little b equals a half. So by changing our point of view, first by translating and then rotating the axes, we really have proved that this curve is a genuine ellipse.
Well, David's procedure can clearly be applied to any second-degree curve. In fact, it could be tightened up to form a proof that any second-degree curve can be put in precisely one of the standard forms of a hyperbola, an ellipse, or a parabola. Well, let's recap how that's done. First of all, we translate to remove the linear terms. Well, if that's impossible, what we have, in fact, is a parabola. But if it's possible, then we know we have a hyperbola or an ellipse, and then we have to rotate to remove this xy term, and what we're left with is a standard form of a hyperbola or an ellipse. Well, all this involves a lot of algebra, but we're going to use all of this algebra to develop a very simple test which will enable us right from the beginning to tell what sort of curve we're dealing with. And I'm sure you'll be very pleased about that. Well, we won't have to do any algebra at all, but for the moment, let's assume that we actually have got to this point so that we know we're dealing with a hyperbola or an ellipse. Now, it turns out that it's easier to see what's going on if we look at the hyperbola or the ellipse from a great distance away, and then we can see what's happening to A, B, or C. Well, let's look at our models again to see what happens when we're a long distance away. Remember I said that when this slicing plane actually went through the vertex, in the case of the ellipse, all we got was a single point. And in the case of the hyperbola, when my slicing plane also just went through the vertex, then what we get is a pair of straight lines. Well, intuitively, if you're very far away from the model, how can you possibly tell if the plane is going precisely through the vertex or not? You can't. So, intuitively, from a great distance, an ellipse ought to look very much like a single point, and a hyperbola ought to look very much just like a pair of straight lines. As we move further from the hyperbola, it looks more like a line pair. Let's thicken the lines so that we can still see them as we move out again. Now, at this distance, you really can't tell that you're not looking at a line pair. Now, if you do the same for the ellipse, well, from this distance, it just looks like a point. So, from a long way away, there's really a very dramatic difference between the ellipse and the hyperbola. Now, is there an algebraic way of expressing this?
Well, yes, there is. In fact, we've seen that from a long distance away, a hyperbola looks like a pair of straight lines. And in moving further away, we're really just enlarging our field of view. To express the curve being further away, I move back, but I take the grid with me. And now I must express that curve relative to this grid. We move back from the curve, but we bring the grid back with us. Move back, and bring the grid back. How do we get from one grid to the other? We'll stop here and look at this point. We'll call it xy relative to our small grid, and big X, big Y relative to our new moved grid. Now little x is 3. But big X is only 1. So little x is 3 times big X. Similarly, little y is 3 times big Y. So as we move out, the factor becomes 4, and then 5, and in general, little x equals r times big X, and little y equals r times big Y. And the larger we make r, the further away we will be. So we need to substitute these equations into the one we've been trying to test. And we get a r squared x squared plus b r squared xy plus c r squared y squared plus h equals 0. Well, we can divide by r squared to give us a x squared plus b xy plus cy squared plus h over r squared equals 0. But we're really only interested in large R. And if r is large, then h over r squared is very small. So if we make r large enough, we can ignore h over r squared. We want to know if this equation is a point or a pair of lines. Now the equation of a line is y equals mx. Can we rearrange our equation to read y equals something? Well, we can look at it as a quadratic in y, and we can use the formula to solve it, which gives us y equals something times x. And there are two values of the something, one for plus and one for minus. So if this rearrangement works, we do have two straight lines. But the formula only works if b squared minus 4ac is positive. And that means b squared is greater than 4ac. So we can tell if b squared is greater than 4ac, the equation represents two straight lines, so our curve is a hyperbola. But if b squared is less than 4ac, then the expression inside the brackets isn't real. So only x equals 0, y equals 0 satisfies the equation, and then we have an ellipse.
So we know that at this stage we can use that pretty little b squared minus 4ac test to discriminate between the hyperbola or the ellipse. For example, if b squared is greater than 4ac, then we have a hyperbola. And if b squared is less than 4ac, then we get an ellipse. I bet you're wondering what happens when b squared is equal to 4ac. Well, in that case, we get the parabola. Because it can be shown this is precisely the case where you can't lose the linear terms by translating. So in fact, we could apply this test at the beginning to show that we can't get rid of the linear terms. Actually, the test is even more powerful than it looks, because remember that when we translate to remove these linear terms, we didn't change the value of a, b, or c. So we could really apply this test at the very beginning to tell whether we have a hyperbola, an ellipse, or a parabola. So David could actually have used this test from the outset to show that he had an ellipse.
Well, that's right. If I'd calculated b squared and 4ac right at the start, then I would have told immediately that this curve is in fact an ellipse. Well, let's just check that. B squared. Well, b is about minus 72, say roughly minus 70, so b squared is approximately 70 squared. And 4ac, well, 4a is roughly 200, and c is again roughly 70, so this side's about 200 times 70, and that's much bigger than 70 times 70. So b squared is less than 4ac, so I know without any further work that the curve's an ellipse. Well, there you are. You've got a very simple test which will tell you virtually at a glance what sort of curve a really horrible equation like this represents.